Okay. Hi, everyone. Thanks for coming to this talk. My name is Dmitry Matveyev, and I'm a deep learning researcher for the last 5 years. So today I will present a topic on scientific approach to deep learning. Okay. How do I switch? Okay. So the traditionally model tuning can be described as a flowchart on the right. You usually start with some baseline, and you can get some initial results. And then you might want to meet some requirements because you participate in some competition, or you want to improve your results to satisfy your customer needs or something like this. And there are going to be a cycle of improving model or tuning hyperparameters, and this cycle will continue until you will meet either top place in your competition or meet requirements of your clients. So the ultimate goal of model tuning is just to find a set of hyperparameters that maximizes the performance of the model. And there can be two additional time requirements. One is you either have a fixed deadline because you participate in some competition, or you do it continuously because you just want to improve your model in production to get better than your competitors. But there are two main problems in all this thing is that first of all, one step of this iteration is quite long because it's training of neural network. And if you have very big data set or very big model, it might take not a couple hours, but a couple days or even a week. So iterating takes a lot of time. And second of all, the hyperparameter search space is extremely large. And it means that if you need to iterate over 1,000 times in doing random search, it will take you forever to find a very good model. Yeah, so maybe there are some ways to optimize all this thing. And let's dive deeper. Okay, so the most common approach is just use some automatic model tuning. There are automatic hyperparameter search algorithms such as random search or grid search, or smarter algorithms, for example, Bayesian search. But again, the problem is we still have very large search space of all hyperparameters. And these algorithms, they require require a user to specify the search space. And it means that, and second of all, performance results of this optimization algorithms largely depend on the search space that you define. Yes, so in this case, with the automatic model tuning, we have a human in a loop, and maybe we can also optimize behavior of a human in some way. So maybe there are some strategies that human can use to further reduce the hyperparameter search space and overall improve the final results that you can get. Yeah, so ideal better strategy will have three main features. One is it reduces search space. Another one, it may suggest you potential new features to try. So some modifications to your model and some strategies for the data preprocessing augmentation or something like this. And last one, it overall can help to reduce training complexity and speed in a way that maybe you will find that some of your algorithms or some hyperparameters are completely useless, or some parts of your model don't influence performance of your model. So you can just remove them and it will speed up your training a little bit, or maybe even a lot. And as I said before, on this slide, we have a loop. So speeding up this loop can help you a lot with achieving better results. Yep. So there is a more scientific way of model tuning. And the scientific model tuning, the main goal is to improve speed of this iteration over here, or optimize choice of the hyperparameter tuning. So first of all, you need to start with a very simple baseline, not just any baseline, but a simple baseline, such as, for example, the most common choice for the image classification models will be something like ResNet, because it doesn't have a lot of hyperparameters, and it's not a very complicated model, but it's very easy to change its size and etc. And should be very relatively easy to optimize hyperparameters, right? And then we start doing incremental improvements on our hyperparameter set in a way that first you design some experiment, build up, get results from the experiment. Based on the results, you can build some insight onto your problem and maybe understand better what hyperparameters result in a better performance and what hyperparameters don't work at all. Yeah, and any recorded improvement on hyperparameter set should be based on a strong evidence. And what it means, what all these three steps mean, we will discuss on the next slides. Okay. So, primary goal. With the most commonly used tuning strategy, primary goal will be just to try optimizing or maximizing performance of the model on a validation set or test set as fast as possible by just random search or by Bayesian search. The problem of this approach is that you can end up in a situation as this penguin. If you participate in some competition, you may get a hyperparameter set that gives you top 3 accuracy in the competition, but then you slightly change hyperparameters and the performance of the model only drops and it never gets better. And some time passes by, your model is not top 3 anymore, it's maybe top 5 or top 10, but you cannot improve your results anymore because you just keep using random search or something. Yep. Okay. Or second approach will be you can spend some time or majority of your time trying to gain insight of your problem in a way that you try to understand how each part of your model influences performance of the model on the validation and test set. And this approach will help you to reduce the hyperparameter search space because you will understand better how each hyperparameter works in your particular problem. It also will reduce the time to achieve the best performance by reducing number of training loops. And it also will maximize your chances of finding the better model because the better you understand your model and overall problem that you are trying to solve, the more your chances to find the better solution. So primary goal should be not to get as best performance as possible, but to gain insight into the problem. Okay. So insight or short-term goals versus long-term goals. If you prioritize gaining insight over your problem and over short-term gains, you will, again, as I said before, reduce search space, and you will reduce search space of all hyperparameters in 4 different ways. One is that you may find hyperparameters that affect the validation error the most or affect performance of the model the most. And you may focus only on this hyperparameter. Sometimes it can be only like 2 or 3 hyperparameters that increase performance of your model. And it's way, way easier to do random search or Bayesian search over 2 or 3 parameters. And you also can find some hyperparameters that are almost insensitive to changes, and it means that you can just fix them in next experiments and ignore them in when you set search space for your optimizer, such as random or grid search or Bayesian. And also, you may find some hyperparameters that interact with each other and with each other the most. And it means that whenever you tune one parameter, you also need to tune another to get good performance. Otherwise, you will try tuning one, but not tuning another one, and it will end up not in a good way for you. And all these 3 together, they will overall just let you find a smaller range of more optimal values that will totally reduce search space a lot. Okay. And overall, while you are trying to get insight into the problem, you may find some potential new features to try and maybe implement some new parts of the model, end up with a very good performance, maybe even write a paper or something like this, or maybe make your customer very happy because you have state-of-the-art model. And also, I'll show later, you may be able to reduce training complexity and speed of the model by removing some parts that don't contribute to performance at all. Okay, so one more argument towards of the scientific way of deep learning tuning is that all components of neural network training pipeline can be grouped up into basically like 4 parts. One is data, and data can be split into something like feature engineering, data preprocessing, and data augmentation. Another part is model architecture that has some layers. Each layer has its own size, hyperparameter, activation functions, and regularization, such as dropout, L1, L2, something like this. Another component is optimization part that is made of optimizer, loss function, some performance metrics, and last part is training that just changes your training speed or something like this, number of epochs, batch size, etc. So if you look at this, you can focus your experiments on each component of your neural network pipeline and try to understand better how each part of the component works. So it's some sort of a first principles approach where you decompose your problem into smaller components, and it doesn't look like a chaotic number of hyperparameters anymore. If you understand how each part works, then you will have easier time to make very small set of hyperparameters that you need to tune to get a better result. Okay, so this presentation is focused on this. How do you get better results in a shorter time, maybe? Okay, so I need to introduce some terminology a little bit. So first one, in this deep learning tuning strategy, there are going to be 3 types of hyperparameters, because for every round of experiments, you will end up with the 3 types of hyperparameters. One type is scientific, and the goal of experiment is to measure how scientific hyperparameters changes model performance. So you measure only one part of the model, for example, how particular data augmentation influences model performance, and this data augmentation will be your scientific parameter. Second type is nuisance, and nuisance hyperparameters are hyperparameters that need to be tuned for fair experiment. By fair experiment, I mean, if you change a batch size, if let's suppose that your scientific parameter batch size, which is a not good idea, but anyway, with different batch size, your model can converge at different time. And it means that for your nuisance, you should have a epoch number. So you need to tune some parameters such as epoch number, for example, for a fair experiment. Otherwise, with batch size 32, batch size 128, your model may converge with different epochs. But if both experiments are run with the same number of epochs, it's going to be not fair experiment. And last one is fixed hyperparameters. And these hyperparameters are just some hyperparameters that you can fix and forget about them for the run of this particular experiment. Okay, so I'm going to show some examples, and for better understanding what are these 3 types of hyperparameters, because it can be sometimes very hard job to determine hyperparameter type for each component of your neural network, because each hyperparameter type is not inherited by its nature. It changes based on the experiment objective. And here I put example that activation function type of a hyperparameter is based on the objective of the experiment. So if your experiment goal is to find what is better activation, ReLU or tanh, then your activation function will be a scientific parameter, because goal of your experiment is I want to check what model performs better if I use ReLU or 10H. And if your experiment goal is, I want to find the best 5-layer or 6-layer architecture of the model, in this case, your activation function might be a nuisance parameter because for different architectures, you might need to change activation function. Otherwise, it won't be very fair. Okay, and last one, if your experiment goal is, I want to check how different learning schedules affect model performance, then your activation function has no correlation with this experiment goal, and you need to fix activation function for all the experiment runs while you are changing your learning rate schedules. Okay, so let's check 3 examples of experiment goals and how what 3 hyperparameter sets we can set for them. So first experiment example is experiment goal is how adjusting model size changes model performance. In this case, our parameters that we want to measure, scientific parameters, are number of layers and number of neurons in each layer or size of each layer, right? Because again, the goal is how model size affects model performance. Nuisance parameters in this case are going to be training time, learning rate, and regularization parameters, because if you increase your model, a bigger model may need a longer time to converge, or with a bigger or smaller model, you might want to change learning rate to scale it accordingly. And bigger model have higher chance to overfit on a trained data, and it means that you need to increase regularization. Otherwise, you will end up with a overfit model, right? So, and fixed hyperparameters are going to be something like activation function, optimizer type, loss function, and etc. So the only thing that we are interested in measuring is number of layers or the size of each layer, and everything else should be fixed, or we need to adjust how long the model needs to converge. Otherwise, it won't be fair. Second example of experimental objective is trying new data augmentation. So our goal of experiment is let's try a new data augmentation, and scientific parameters or measurable parameters will be data augmentation type and parameters of this data augmentation. In other words, it's just intensity of augmentation or probability of selecting this augmentation. Nuisance parameters going to be something like learning rate, number of training epochs, and early stopping criteria. You need to adjust number of training epochs or learning rate because if you introduce some new data augmentation, your model may need, again, longer time to converge because data augmentation is regularization. And fixed parameters are going to be model architecture, optimizer type, loss function, etc. Okay, and last experiment example is your experiment objective, your experiment goal is to test how different optimizer types affect the model performance. So your only scientific parameter is going to be type of optimizer, such as ADAM, SGD, RMS prop, etc. And nuisance parameters in this case going to be learning rate, momentum of your optimizer, beta values. So parameters that you need to tune between for each optimizer. And fixed, again, as in previous time, going to be model architecture, activation function, loss function, etc. Okay, so the main point is you want to measure only one part of the model, and other parts should be either tuned to make experiment fair between different runs, between each run, or you just fix parameters because they have no relationship to your experiment goal. Yeah, so we have some better tuning strategy, and we can run multiple experiments and maybe gain some insight, but we have a problem that conclusions or insights that you gain for a set of fixed parameters, they work only for the fixed parameters values that you used. For example, if you found some good set of parameters for batch size 32, and then you change your batch size to 64, most probably and most definitely your results and your insight will not work for batch size 64. Yes, so there is one problem is if you have some set of fixed hyperparameters, you need to remember that you run your experiments only for these values. And once you change them, you need to rerun everything again. So one good one recommendation about batch size, for example, and especially for batch size, is batch size should not be used as an optimization parameter. You need to choose batch size as some fixed value in the beginning, and then better not change it. Because if you change it, a lot of your experiment results will be completely different. Okay. So it's all good, but how do we choose the goal for the next experiment? And each experiment should have a very clear goal, such as I listed before, how different optimizers affect the model performance, how particular one data augmentation type affects the model. If you throw 5 or 10 different augmentations and run experiment with all these data augmentations, it will be very hard to separate effects of each data augmentation. Yep. So bad example is mixing data augmentation and some other regularizations like dropout, and you will get some results. Maybe you will get even good results, but it will be hard to separate, was it actually data augmentation or dropout values that improved your performance. And good examples are as a separate goal can be try to find better regularization techniques, try new data preprocessing, or test different activation functions. Yep. So simplicity is a key. And next part is as I showed before, there should be some incremental tuning steps. And when Sam Altman was asked how did they achieve such a good performance of ChatGPT and GPT-4, in many interviews he answered that OpenAI team is very good at incremental changes. So incremental small steps, they might be the key for your good performance and for winning competitions or satisfying your customers. Yeah. So incremental steps in this tuning strategy are going to be, first, you need to identify goal for the next round of experiments, such as I listed before. You need to design and run a set of experiments that will progress you towards this goal, and you need to choose a scientific nuisance and fix hyperparameters for the experiment somehow. I will talk a little bit more about this part because when you are just starting, especially if you are just starting, it's very hard to understand, is it scientific parameter, is it nuisance, is it a fixed, especially for nuisance and fixed hyperparameters. So a couple slides later, I will give you some ideas about this. And next step, third, is learn from results and consider if you need to update your best set of hyperparameters, and repeat this process again and again and again. And I will talk a little bit more about the step 4 and 1 and 2. Okay, there's going to be a lot of text again. So as I said before, we always start with a very simple baseline, and we incrementally add features and make improvements. We design experiment, and after we design experiment and decide on fixed hyperparameters, scientific or nuisance, usually it takes a lot of time to run experiments by yourself manually. So it's better just to set up automated search algorithms for each round of these incremental steps, incremental changes, and just set a hyperparameter search for your scientific parameters, and that's all. And also adjust nuisance parameter accordingly. Get results from all automatic search, and based on the automatic search, you can get build up insight into the problem. And there are some ways how you can visualize the results of your experiments. I will talk about it on next slides again. And after this, you just update search on the new insights that you gained and repeat these experiments again and again and again. So yeah, whenever you update the best configuration, your update should be based on strong evidence, and it's not a good idea to include into your updated set of hyperparameters some lucky random configuration that led to a very big or just a little bit improvement of performance, but you are not sure why this lucky configuration works. Yeah. And the main strategy how you can actually decide when to update the best model configuration will be explained on the next slide. But first, I need to describe what is trial variance. There is such thing as trial variance, and this variation of experimental results, it can arise just from the different random seeds. And this happens if you didn't set up random seed, or if you changed some combinations of your algorithms that use random sampling. And some parts of algorithms that use random seeds are random initializations of your weights. You always initialize weights with some random distributions by sampling from random distribution. You shuffle data for train validation split and also shuffle your training batches. Your dropout masks use random seed, and data augmentation sometimes use random seed. For example, you can apply some augmentation with some probability. So the point is you can choose new configuration as the best model or the best set of hyperparameters only if this set of hyperparameters, first of all, shows a real improvement, and second of all, it doesn't change if you change your seed. So if changing seed with the same set of hyperparameters changes model performance a lot, it means that this set of hyperparameters is just like a combination. And the problem will be whenever you change your algorithms. Okay, so one solution will be, okay, let's run everything with the same random seed all the time. Let's just fix a random seed for reproducibility. That might work for this new lucky set of hyperparameters. But if you add some new data augmentation that uses random sampling, or you change way in which you first initialize random weights and then do data shuffling, or you switch this to things, you will change random values that are sampled from random distribution, and you will end up with a bad performance. So again, whenever you get some good result, it's a good idea, and you are about to go for the next experimental steps. It's a good idea to run this experiment with different seeds, just to make sure that changing random seed doesn't change model performance a lot. It can vary a little bit, but not a lot. Yep. Okay. As I said before, every training step takes quite a lot of time. So, and a lot of people don't have a lot of GPUs and a lot of time. So there can be some additional steps that you can use to optimize your training time. And there are some hyperparameters that change training time of your models because they increase gradient variance. And these hyperparameters are smaller batch sizes. So if you get some good performance with the smaller batch size, but you need to speed up, maybe it's a good idea to initially choose a bigger batch size. Yeah, and another is some data augmentations. So a lot of data augmentations, they take quite a lot of time, and I mean, just to do pre-processing, or because it's regularization, they can increase time that you need for the model to converge. And last one is a lot of other regularizations like dropout. If you heavily regularize your model, but you are limited on the time, that might be a not good idea. So maybe you need to decrease regularization and increase batch size if your GPU allows it. And this way you will be able to increase training time a little bit. And maybe you can also decrease model size, because yes, big models is good, but maybe if you decrease model size and be able to iterate faster, you might be able to get the good results faster and with a higher probability, because you have more time to check different hyperparameter sets. Yep. So as I said before, once you set up some experiment, it's better to run hyperparameter sweep. And on this slide, you can see some examples. If you are using Keras or TensorFlow, there is Keras Tuner. If you're using PyTorch, you can use the one that is suggested by PyTorch documentation. It's called Ray Tuner. Another one is there are a lot of commercial solutions, and I really like weights and biases. They allow you to do hyperparameter sweeps, log your trainings, etc. But the warning is, if you are using this project for a company, you might need either pay money or it's limited by only 100 hours. Yeah, so it's a good for using for participating in competitions, but can be expensive if you are using it for work. And also, as I said before, when you are running different experiments, you are interested in gaining some understanding how different hyperparameters affect performance. So some hyperparameter search libraries, they also let you output correlation between your hyperparameter and model performance, and also between different metrics. For example, you can choose validation loss or number of epochs that your model needed to reach the best validational loss or best validation accuracy, or whatever is your metric. And they usually just show you a linear dependency between the parameter and the chosen metric. So for example, here, applying higher weight decay will result in a better performance, or lower weight decay will result in a lower performance. And encoder size has lower correlation than other 4 parameters. Yeah, so it might be, again, a good idea to use some hyperparameter sweep libraries instead of doing it manually, because these libraries will have this additional function where they will help you with gathering statistics between correlation and between hyperparameters and the model performance. Okay, so all this looks very complicated, and it's very hard to understand how to start, especially if you are only starting in neural networks. So the good strategy to start will be, again, to write down all components of your neural network model and training pipeline, such as I did on the earlier slides. So there are 4 main components, or maybe in your case will be 5 or 6. And for each of the big components, it's a good idea to write down all the subcomponents, and then design experiments that test each small components, such as how optimizer affects model performance, how number of epochs affects model performance, or how number of layers and the layer sizes affect model performance, etc. And there are going to be next step, which is how do I choose which parameters are scientific, which parameters are nuisances, and nuisances, and which parameters are fixed. And there are 2 answers for this. One, well, it just comes with experience and understanding of neural networks. If you have some supervisor or a friend who is working in deep learning for longer than you are, you can ask them. Another way is you can actually consult with ChatGPT, GPT-4, or any other big language model. They are actually very helpful with this problem. And after you have experiments, you just run hyperparameter sweeps for designed experiments and repeat this process until you get desired results. Okay, and some additional tips and tricks. Whenever you start with a simple baseline and you just start trying to solve some problem, it might be a good idea to train on a subset of a data for example, only one batch or like 20 images if you do image classification. Turn off all the regularization and check if the model achieves perfect accuracy if you are doing classification, or just perfect performance metrics. Because if your model cannot achieve best perfect results with a very small batch, it means that there is some problem with your code, and you need to double check everything. Yep. Also, another sanity check is increasing the regularization strength, such as dropout, L1, L2, weight decay, or data augmentation, should increase loss value. And the next one is, it's a very good idea to visualize your data before and after preprocessing or data augmentation, because sometimes you implement some custom preprocessing algorithm or some custom augmentation, start running model, it looks like something is wrong, and you decide that this preprocessing doesn't work or this augmentation doesn't work, but then later you realize that the problem was not in the model interaction with this algorithm, but just algorithm didn't work correctly. Yeah, and it's very good to visualize your loss and performance metrics history for train and validation splits all the time, so you can check, you can always catch if your model overfits or underfits or something else, or just behaves weirdly. Yeah, and some recommendations from Karpathy, Andrei Karpathy from 2018. So there are some common errors or problems that you can get. One is, again, you didn't try to overfit on a single batch first, and if your model cannot overfit on a one small single batch without regularization, then you have a problem, as I said before. And some problems just related to the code, such as you forgot to toggle train or evaluation mode for the network if you're using PyTorch or TensorFlow or some other deep learning frameworks that support toggling from train to validation modes. If you're using PyTorch, you forgot to use zero-grad, and your gradients are coming from previous epochs, which will screw up your backpropagation. And last one that may happen quite often, especially if you switched from Keras or TensorFlow to PyTorch, you pass softmax logits instead of raw logits, where your loss function expects raw logits. Yep. Let's see if I have more slides. Yep. Here are some resource recommendations. One is there is Coursera specialization that is called Deep Learning Specialization. And the second course is focused on the deep learning, fine-tuning, and hyperparameter search. There is also a GitHub page from the Google research team that is called Deep Learning Tuning Playbook, and it covers these materials that I talked about today and more materials in more depth. And another blog from Andrei Karpathy that just has some short recipe to how to train good neural network that also includes similar strategies. And that's all. Thanks for listening. I will be happy to answer any questions if you have any questions.
Hello, everyone. If there is not any questions, we'll probably go ahead and end the stream in a few minutes. And then thank you all very much for coming. As we mentioned, or as I mentioned during the opening ceremony, we've got a couple more fun streams and mini events planned for the rest of the week. So I hope to see you there. Thanks, y'all.
Thank you very much.